Last time we talked about sampling, sample distributions, and finally talked about central limit theorem. And as I indicated several times during those discussions, not simply the last meeting, but for the first part of the semester, we were simply going through the box. Making sure we had all the parts from Sears for the garage door opener and identifying what those parts were. We're going to start today discussing hypothesis testing, which is the basis of social research. And we'll start with the most straightforward example of hypothesis testing. We will spend very little time on this, and it won't be part of the exam. And the reason why we will spend very little time on it, and the reason why it will not be part of the exam, is because researchers, at least in communication, typically do not undertake this sort of research. Let's imagine that you have initiated some sort of program for commuter students. A program that you think and expect will improve the academic performance of commuter students. Let us suppose further that because you recognize that performance in a history class may be different to performance in a math class, you have chosen a specific class or type of class to test the effects, in which to test the effects of your program. Let's say that you know that the average GPA of all commuter students taking this sort of course is 2.78. And let us presume further that you know that the standard deviation of those scores is 1.95. You now select a sample. Well, let's go back before you select your sample. What is your research hypothesis, represented by uppercase H subscript 1? What is your research hypothesis about the relationship between X bar That is the mean of the sample that you're going to examine, a sample of people who have been commuter students who've been through your program, and mu, the mean GPA of all commuter students taking this particular sort of class. What do you anticipate is the relationship between those two scores?
It should probably show equality, or either equality or not equality.
Well, if you say they should show equality or non-equality, you've covered all possibilities. You've got to cover only part of the board here.
I was going to say, if the commute is longer, then the GPA is less.
You would speculate that the average GPA of the sample who have been through your program will be less than the average GPA of commuter students in general?
I'm just saying, if they have longer commute, maybe they miss more classes.
Perhaps I haven't explained this very well. You have a population comprised of all commuter students who take an introductory history course in a given semester. And what you have done is you have selected a subset of that population, and they have been through your program. And the program is designed to improve the academic performance of commuter students in history courses, basic history courses. Wouldn't you speculate, wouldn't you hypothesize that the average GPA of the students who've been through your program will be higher than the average GPA of commuter students in general? Since your program is designed to improve academic performance, your expectation surely, your prediction surely, would be that the academic performance of those students who go through the program would be higher than the academic performance of commuter students in general. Let's then presume that you measure somehow the academic performance, you measure the GPA across these courses of your sample and discover that it's 2.99. The issue is not whether X bar is greater than mu, because clearly 2.99 is greater than 2.78, which would lead you to conclude, if this is where the process stopped, you would conclude that your program was successful. Would you agree? Would you conclude that beyond reasonable doubt that your program was successful? The broader question is, how would you go about testing the effects of your program? And let's note immediately that there's something called the null hypothesis. And the null hypothesis in this case is that X bar is less than or equal to mu. That is, the null hypothesis the null hypothesis is the opposite of the research hypothesis. Let us also note that it's the null hypothesis that you're testing. And we will talk about these issues in greater detail momentarily. But what I'm trying to do is use the most simplistic form of hypothesis testing to show you something of the bits and pieces that are involved and the process that you have to follow. Let's think about the sampling distribution of sample means. Let's invoke central limit theorem. What is the shape of the sampling distribution of sample means drawn from this population? Let's ask another question. What were the short-term causes of World War I? I just thought you might like to talk about something else. You know. Let's go back to the original question then. If you think about central limit theorem, what is the shape of the sampling distribution of sampling means for a population of scores with a mean of 2.78 and a standard deviation of 1.95? Pardon? No, you need to tell not just me, you need to tell future generations by pressing down on the button.
Is it Bell? Normal distribution? No?
Is it? Pretty sure. Pretty sure. We have one suggestion that the distribution of scores, the sampling distribution of sample means for this population is normal. Doesn't central limits theorem say that if repeated random samples are drawn from a population with mean equal to mu and standard deviation equal to sigma, and if sample size is large, that the resulting sampling distribution will have a mean equal to mu, a standard deviation to sigma equal to the sigma over the square root of n, and it will approach normality even if the population is not distributed normally? It's normal. The sampling distribution of sample means is normal, and it has a mean equal to mu. In this case, it has a mean equal to 2.78, and it has a standard deviation equal to 1.95. We have selected a single sample from this population, and let us assume that n is large. Let's assume that n equals 200. And by convention, the distinction between large and small samples, any sample size of 100 or greater is considered a large sample, and any sample size lower is considered a small sample. So we have a large sample. We have a situation here that would seem somehow to be linked to, or a situation here in which we could somehow link the information that we have to central limit theorem. We now have a sample mean of 2.99. How could we go about determining what proportion of scores in this distribution is lower than 2.99? How did you do it on the exam? This is not a quiz show. It's not a game. You took an exam on this just a couple of days ago. If you don't understand the material, it's time to abandon ship. It's time to abandon the race. Get off your bike, turn in your bike, get in the ambulance. How did you go about determining the proportion of all scores in a distribution that were below a specific score? Just tell me. You first of all standardized the mean score that you had, or the individual score. In that instance, we were talking about individual scores, XIs, and a population. We're doing precisely the same here, even though we're using X bar and mu. The individual scores in this sampling distribution are means rather than the individual scores of individual people. So it seems to me, and perhaps to one or two others, that we could standardize this mean score. That is, we could convert it into a z-score. And to do that, we would subtract from X bar the mean, and we would divide by the standard deviation. That is 2.99 minus 2.78 divided by 1.95, which is 0.21 divided by 1.95, which is approximately 0.10. Would you agree? It's 1.95 is almost 2, so 0.21 divided by almost 2 is almost 0.10, somewhere around about there. I can't do this math in my head, and it's unnecessary. We could now, would you agree, go to table A in the text, look for a z-score of 0.10, which is on page 336. Is that right? And it would indicate to us that 3.98% of all scores was between the mean and z. That is, in this area here is 3.98% of all scores. But we have to remember that this distribution is symmetrical around the mean because it's normal, so that in this area here there is a further 50% of all scores. So that we would conclude that a score of 2.99 which is associated with a standardized score of 0.10, was in excess of 50 plus 3.98% of all scores. So it's above 53.98% of all scores. Which means that the area in here is 46.02% of all scores, or 0.4602 of all of the area under the curve. Yes? The question is whether your program has significantly raised the score of commuter students in general. That is, has it raised is this score of 2.99 significantly different from the mean of 2.78? How confident do you want to be in your decision? How confident do you have to be in order to reject the null hypothesis? Pretty confident? When you go to a physician, the physician's null hypothesis is there's nothing wrong with you. The null hypothesis is that you are healthy. In order for the physician to reject that hypothesis and conclude instead that you are in some way or another unhealthy and prescribe for you a specific course of treatment, how confident do you want that physician to be? Very confident? Beyond reasonable doubt? You find yourself charged with a crime, and you find yourself in a court of law, and the evidence is presented. The jurors go off to decide your fate. You are now confronted, let's say, with one of two possibilities: a return to the life of happiness and security and tranquility that you once had, or becoming the close friend of some really big guy or big woman for the rest of your life in prison. Before that, in order for that jury to reject the null hypothesis, and in a court of law, the null hypothesis is that you are not guilty. In order for them to return a verdict of guilty, do you want them to be sort of certain that you're guilty? Do you want them to have flipped a coin? Heads they're guilty, tails they're not. Well, it's heads, you know. Yes, Your Honor, we found the defendant guilty because we flipped a coin and it came up heads. Or do you want them convinced beyond reasonable doubt? I think the normal standard is convinced beyond reasonable doubt. And so that you understand that this is not just the business of researchers or physicians or attorneys and jurors in courts of law. When you make that big social statement to a relational partner, I love you, one of two things, one of several things can happen. You can get no response. You can get, and I think you're special too. Or you can get the I love you response. before those words come out of your mouth, how certain do you want to be? How certain do you have to be that you're going to get the I love you too response? Very confident? Because as Seinfeld says, that's a pretty big matzo ball to leave out there. Yeah? My point is that we all go about this business of decision making, not just social scientists doing their research, not just jurors in a court of law, not just physicians in their office. We all do it. And particularly when the decision seems to have significant consequences, we seek to be convinced beyond reasonable doubt that the predicted outcome will occur. That is, in order to reject the null hypothesis that you're not guilty, the null hypothesis that you're healthy, the null hypothesis that your partner is not going to give you the desired response. In order to reject that null hypothesis, you have to be convinced beyond reasonable doubt. I do not know what in your heads comprises beyond reasonable doubt. But in social research, that typically is taken to mean being willing to take a 5% chance of being wrong or taking a 1% chance of being wrong. We will see, and don't worry, these pieces will come together. This is associated with something called alpha. Alpha is the willingness to commit a type 1 error. Alpha is the willingness, a researcher's willingness, to commit a type 1 error. We will talk momentarily about alpha and type 1 errors and type 2 errors. Let's, however, first of all, work through this example. In this example, since the research hypothesis is not simply one of difference, that is, the research hypothesis is not that X bar will simply be different to mu. Our research hypothesis was that X bar will be greater than mu. Let us say we're willing to take a 5% chance of being wrong, of committing a type 1 error. What that means is that in order for us to reject the null hypothesis, this null hypothesis, and conclude instead that our program produces, conclude instead that X bar is significantly greater than mu, and therefore conclude that our program has some significant beneficial impact. This particular mean has to appear in this area, an area that contains 5% of all scores. How many standard deviations then does a score have to be removed from the mean, be in a range that contains only 5% of all scores? How about we go to table A? How about we go to table A and look not for particular z-scores, but look for an area beyond z of 5%. If we do that, would you agree, we're on page 337 in the last column. We have 4.95 and 5.05. And let's be conservative and choose the 4.95. That would indicate that for a score to be in this shaded range, it would have to be at least 1.65 standard deviations above the mean. Our score is 0.1 standard deviations above the mean. On that basis, would you conclude, well, let me step back and rephrase it. Would you A, reject the null hypothesis and conclude that your program produces no statistically significant effect? Or would you B, fail to reject, no, let me get this right, would you, because I've got them in my head the wrong way, I've mixed and matched. Would you A, fail to reject the null hypothesis and conclude that your program produced no statistically significant effect? Or would you B, reject the null hypothesis and conclude that your program produced a significant improvement in scores? How many of you would reject the null hypothesis and conclude that your program had a significant effect? Just put up your hands. 1, 2. How many of you would fail to reject the null hypothesis and conclude that your program had no statistically significant effect? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, maybe 15, maybe 16. How many of you would say, I'm not sure, but you're going to tell us in a moment? Well done. Well done. You would fail to reject the null hypothesis. You would conclude that your program has no statistically significant effect on student scores. Before we go over the constituent parts of this, you understand that when you define this extreme area under the curve as the area in which your score must appear for you to conclude significant difference, for you to reject the null hypothesis, what you're looking for is Quasimodo. Actually, what you're looking for in this case is Denzel Washington and Brad Pitt and the rest of those perverts. No. I didn't mean that last part. I didn't mean that last part. They're all great guys, and I'm sure I would get along well with all of them. And I don't hold any jealousy or envy or animosity in my heart at all. You're looking for a score that is significantly different from the mean of 2.78. What this indicates to you is what should be intuitively clear to you, perhaps, that 2.99 is not a whole lot different from 2.78. The issue is not simply, is there difference between the two scores? Because it's almost inevitable that there will be difference between the two scores. Because you're reaching into a population and selecting a sample, and you're going to get some fruit and nut cases in there. You're going to get some deviance in there. So the issue is not simply one of difference. The issue is of statistically significant difference. Just as in a court of law, it's not, the issue is not, do you think this person is guilty? The issue is, are you convinced beyond reasonable doubt? In this case, the simplest form of hypothesis testing, where you're comparing a single sample mean to the population mean, mu, is a case in which you would conclude that there is no statistically significant difference between x bar and mu. That is, you would fail to reject the null hypothesis. You would be forced to conclude that your program produces no significant positive effect in the performance of commuter students in history-related coursework. Before we go any further, let me just make a couple of observations. First of all, we've seen some constituent parts of hypothesis testing. Most obviously, some parts that directly relate to central limit theorem. I indicated at the time that central limit theorem was worth, in and of itself, the price of admission. In fact, you should be giving me more money for me telling you about central limit theorem, because it is the basis of all social science research. It is the basis of all research at some level, because it is that magical piece that connects the thing you know about but don't care about, the sample, to the thing you know essentially nothing about but care dramatically about, and that is the population. Do you understand that when you conclude that there is no statistically significant effect of your treatment, you have generalized across people, places, and settings, people, places, and times. You haven't simply limited your statement to the sample at hand, the people who went through your course. You haven't limited your conclusion to some period in time, and you haven't limited your conclusion to some particular set of circumstances. You have concluded generally that this particular program produces no significant improvement. That is, you've generalized from a specific group in a specific context at a specific time to all people in all circumstances at all times. You have generalized across populations of people, populations of settings, and populations of times. That's the research process. Third, we identified other little bits and pieces along the way that seemed to be critical to research, one of which was the null hypothesis, another of which was alpha. And we will talk about those momentarily. My final observation is, I do not care how complex hypothesis testing becomes, you're always in this same process. That is, the process that we used to make the simplest of comparisons, a single sample mean to a population score, is precisely the same process that you use in other, much more complex research settings. Yes.
So, for example, if we changed X bar from 2.99 to 1.65 for the Z-score, then that would mean that that would be a significant change towards mu. Because
if this raw score, original score, when we standardized it, generated a standardized or Z-score of plus 1.78. That is, it's somewhere up in here. Yes? We would then reject the null hypothesis. This is a Brad Pitt, a Denzel Washington, whoever else is out there and cute and cuddly. Not cute. Cute is somewhere in here. Yeah, you're cute. This is knockout stuff. This is knockout stuff. This is stuff you cut off your right leg and thank God or the gods above, that that's all you had to do to get this person. Because you'd have done more. You're looking for statistically significant difference. You're looking, on the one hand, for the Denzel Washingtons and the Brad Pitts and whoever else. Is Matt Damon in that group? Or is he? No. Matt Damon's not in that group. What about Leonardo? Is he in that group? No? Well, tell me somebody else is in that group. I've got to update my data bank. Pardon?
Patrick Dempsey.
Patrick Dempsey. Who's Patrick Dempsey?
Grey's Anatomy.
Oh, I don't do Grey's Anatomy. Patrick Dempsey. You're looking for Patrick Dempsey. Or you're looking for Quasimodo. You're looking for the Elephant Man. You're looking for things that are significantly different from the mean. Significantly different from the average. In order to be convinced beyond reasonable doubt that there is a real difference, and not simply a difference that will occur by chance. This is my favorite part. Oh God. You know that cleaning a house can be this easy. You just get a maid service. I know that because for my birthday I treated myself to a maid service. But while talking about my birthday, there were no gifts forthcoming. And I'm pretty disappointed. I'm not pretty disappointed. If I open my heart to you, I'm desperately disappointed. But that's okay. Be selfish. I'll get my own back. Because I set the exams. First of all, alpha. As I indicated to you, alpha is a researcher's willingness to commit a type 1 error. And by convention, that is set at either 5% or in terms of probability 0.05, or it is set at 1% or 0.01. And the researcher decides the level of alpha. The researcher decides the level of alpha. So if alpha is the willingness to commit a type 1 error, what on earth is a type 1 error? Would you agree that we can distinguish between the researcher's decision and what is actually the case? Yes? We can distinguish, for example, between the verdict that a jury returns, the jury's decision, and what is actually the case. No. If a jury returns a verdict of guilty, does that necessarily mean that the defendant committed the crime? Then we can distinguish between the jury's decision and what actually occurred. The jury's decision about what actually occurred and what actually occurred. Yes. A jury can either reject the null hypothesis or fail to reject the null hypothesis. Would you agree? That is, on the one hand, they can reject the null hypothesis and return a verdict of guilty, or they can fail to reject the null hypothesis and return a verdict of not guilty. In actuality, the null hypothesis is either true or the null hypothesis is really, in actuality, false. That is, either the defendant is not guilty or the defendant is guilty. The defendant either in reality did not commit the crime or did commit the crime. Would you agree?
If it's false, do you that means the statement's true or correct? Is that how it works?
Let me ignore that question momentarily.
You don't have to go.
Yeah, I know it. This. Let me go through the complete explanation, because it seems to me that the key difficulty in this discussion is the use of the negative. You approach it from what is intuitively the wrong end. Would you agree that if a jury fails to reject a true null hypothesis, everything is kosher? A jury fails to reject the null hypothesis. They return a verdict of not guilty. In actuality, the defendant did not commit the crime. So everything is rosy, hunky-dory, perhaps a little more hunky than dory. Everything is kosher dill, everything is fine. Similarly, when a jury rejects the null hypothesis and returns a verdict of guilty, if in fact the defendant committed the crime, that is, if in fact the null hypothesis is false, that too is all well and good. The problem occurs in the other two quadrants. When juries return a verdict of guilty and the null hypothesis is true, they have returned a false verdict of guilty, an incorrect verdict of guilty. They have committed a type 1 or alpha error. They have committed a type 1 or alpha error. They have sent the wrong person up the river. Likewise, when a jury fails to reject a null hypothesis and returns a verdict of not guilty, and the defendant actually committed the crime, that jury has committed a type 2 or beta error. They have returned a false verdict of not guilty. Let me stop and ask, are there any questions about this 2 by 2? Yes.
Can you explain the top left the type 1 error one more time?
A type 1 error occurs when the jury rejects the null hypothesis. And the null hypothesis in a court of law is that the defendant is not guilty. A jury that rejects the null hypothesis then returns a verdict of guilty. When the jury does that, the jury can either be right or it can be wrong. The jury is wrong when the null hypothesis is true. That is, when the defendant actually did not commit the crime. And in that circumstance, the jury has committed a type 1 or alpha error. They have rejected a true null hypothesis. They have rejected a true null hypothesis. When a jury fails to reject the null hypothesis and returns a verdict of not guilty, they too can be either right or wrong. And they are wrong to the extent that the null hypothesis is false and in fact the defendant did commit the crime. They have returned a false verdict, an incorrect verdict of guilty. They have failed to reject a false null hypothesis. And in that case, they have committed a type 2 or beta error. And you and I know that juries do this. Sometimes they're right when they return a verdict of guilty, sometimes they're right when they return a verdict of not guilty, but sometimes they return a false verdict of guilty. They send the wrong person up the river. And sometimes they return a false verdict, an incorrect verdict of not guilty. And they let the guilty person go free. on the one hand, and they have committed a type 2 or beta error. More generally, we can talk about a type 1 error occurring when a researcher rejects a true null hypothesis. And a type 2 error occurring when a researcher fails to reject a false null hypothesis. Let's go back to the court of law. In our culture, because when we sat down and designed our system of justice and trial and so forth, we knew this. We knew this. We knew that juries could be wrong in their decision making. So in our culture, do you think that we would, if we are going to commit an error, would we prefer it to be in a court of law? Would we prefer it to be a type 1 error or a type 2 error? I think there's evidence, ample evidence, that if we are going to commit an error in our culture, in a court of law, we would prefer it be a type 2 error. We would prefer to occasionally let the guilty go free than fry the innocent. Evidence of that. We have juries of 12 people. And we don't have just one person. We don't have me go off and flip a coin. Do you know how many guilty verdicts I'd be returning by the end of the day? I'd be like Robespierre. They're all guilty. Off with all of their heads. We have 12 people. What is more, we don't say to them, well, if a majority of you are sort of think that the defendant is guilty, then return a verdict of guilty. We require, under most circumstances, unanimity amongst those 12 jurors, first of all, and second of all, and most important for our circumstances, we require that each of the jurors be convinced beyond reasonable doubt that the null hypothesis is false. We require that jurors be convinced beyond reasonable doubt that in fact the defendant committed the crime before they reject the null hypothesis, which is that the defendant did not commit the crime. In that regard, the same bias exists in social research. But I will say of a court of law, and I will say of social research, clearly in a court of law, we try to ensure that jurors commit neither type of error. And that is true in social research too. But the starting point in that regard is that jurors are instructed to be convinced beyond reasonable doubt. That is, in order to reject this null hypothesis, jurors are instructed that they must be convinced beyond reasonable doubt that the null hypothesis is false. In order to reject the null hypothesis, you must be convinced beyond reasonable doubt. And what does that mean? It means that you establish alpha equal to either 0.05 or to 0.01. If you set alpha equal to 0.05, you are willing to take a 5% chance of committing a type 1 error. If you set alpha equal to 0.01, you are willing to take a 1% chance of committing a type 1 error. We could rephrase this. If alpha is 0.05, that indicates this decision rule. In order to reject the null hypothesis, I must be at least 95% confident that it is false. If a researcher sets alpha equal to 0.01, it establishes the decision rule, in order to reject the null hypothesis, I must be at least 99% confident that it is false. These issues are discussed in the text, not as clearly and not with as much insight as I've discussed them in here. I'm joking. Again. These issues are discussed in the text. I advise that you read the text explanation and you go over your notes. And I advise that beyond the obvious for two reasons. One, this thinking will stay with us for the rest of the semester. This logic will stay with us for the rest of the semester. And second, it will stay with us for the rest of the semester because it is critical, it is fundamental to hypothesis testing. It is fundamental to social research. There is not a person in here who is not capable of understanding this stuff and understanding it easily. But I think to get to that point, you have to be willing to read over the material in the text and read over your notes. And if you have questions about this stuff, to ask those questions when we next meet. Okay? Bon appetit.